Hello everyone. Today I'm going to introduce a lava solar tracker for ocean environment. My name is Ruoyu, a PhD student from the Chinese University of Hong Kong, Shenzhen. I'm also involved in Shenzhen Institute of Artificial Intelligence and Robotics for Society, which is ELS. This is the research under the supervision of Professor Huihuan Qian. I will introduce from these aspects. Solar tracker is a device that is able to align to the position of the sun. In this way, the energy harvested by the solar panel can be maximized. Traditional solar tracker is driven by motors, and according to the number of the degree of freedom, it can be divided into single axis and dual axis. Solar tracker can be applied in ocean environment due to the abundant solar energy source. One example is floating photovoltaic plants. However, traditional solar tracker is a complex structure which makes them hard to maintain and also inefficient in cost. Therefore, we proposed a lower solar tracker for ocean environment, just as shown in this figure. The solar tracker is mounted on a buoy. The shake caused by waves is used to adjust the attitude of the PV module. The device is motor-free, and the attitude of the solar panel can be maintained with low energy consuming. The system can be driven directly, and the drive circuit for motors are eliminated. Therefore, the structure is simple and easy to maintain. Here I'm going to introduce the design of the proposed solar tracker. The proposed solar tracker has 2 degrees of freedom, as shown in left figure. The solar panels, whose attitude can be measured by encoder A and encoder B, are released or locked by controlling the state of brake A and brake B. The brakes are able to lock the spindle or turntable in power off state. The brake we used is shown in the figure below. Different from a servo motor, the brake can be driven directly and is able to engage without power and can be released when the power is supplied. In order to control the solar tracker, we need to know the desired state and the real state of the system. The desired state is the desired pose of the solar panel. It has a relationship with the elevation angle and azimuth angle of the sun, and these 2 angles can be calculated by an offline model with the location and time information. The other information need to be provided is the pose of the solar panel and the pose of the base. This can be easily measured by encoders and IMU. So since we already get all the inputs we need, the only problem is how to control the pose of the solar panel in 2 degrees of freedom by 2 brakes. The strategy is predicting the dynamic at the moment when the brakes are released, and the brakes are released only when the predicted dynamic is going to approach to the desired pose. So we formulate the dynamic model of the system. However, the system is very complex because the base is floating. Here we decouple the system into 2 parts. One part is shown in the left figure. We look into the system from the direction of the rotary spindle, which makes it similar to a double inverted pendulum. The other part is a rotary platform, and we assume that the inertia and mass of the upper part will not change. That is shown in the right figure. In this way, we can get the dynamic model of the 2 parts respectively, and finally derive the acceleration of the pose when the brakes are released. Notice that we need acceleration information. Here the phase-locked loop is applied to estimate the acceleration. At last, this control law is followed to control the solar tracker. We release when the predicted dynamic is going to approach to the desired pose and engage when the angular velocity is close to 0. In this way, the solar panel can be adjusted intermittently, and the control logic is shown in this figure. Note that the model is decoupled, so we adjust 1 degree of freedom at a time to avoid the effect of the coupling dynamics. We also evaluated the energy efficiency by simulation. Harvesting efficiency of the proposed system could be impaired due to 2 problems. One is the poles of the solar panel can only be adjusted intermittently. The other is the solar panel is hard to align to the sun because of the perpetual waves. Here we calculated the harvested energy in 1 day by its model. Theta E is a misalignment caused by discontinuous control, and theta W is a misalignment caused by waves. TSS and TSR are sunset time and sunrise time. The parameters in the red block are deterministic and are related to the illumination and maximum power of the solar panel. In this simulation, 3 conditions are concerned. Condition 1 is solar panel that can be adjusted in real time, which is similar to the traditional solar tracker. Here theta miss always equals to 0. The second condition is like the proposed solar tracker, and theta E can be adjusted intermittently. And condition 3 is the ideal condition where waves will not impair the efficiency, which means theta miss can be adjusted intermittently. A sinusoidal wave is applied to simulate the ocean waves. We will see the value of energy in different conditions with respect to different amplitude and period. The simulation results show that the harvesting efficiency of the proposed system is 95% of that of the traditional dual-axis solar tracker, even when a miss is only 20 degrees. And the loss of the efficiency due to the waves is less than 4% when a miss is less than 20 degrees. This is the experimental platform for parameter tuning and model verification. The solar tracker is mounted on a 3 degree of freedom rotary platform, which can be used to simulate the effect of waves. The properties of the components of the solar tracker are listed in the right table, and the hardware diagram is given in the figure below. We designed 2 experiments in this platform. The first is to input waves in 1 degree of freedom, and the second is to input wave in 2 degrees of freedom to simulate the real ocean waves. In the first experiment, because the input is known, therefore, the real acceleration is also known. We fine-tuned the acceleration estimator and compared the real result with the estimated one to make it more accurate. The results show that the average error of the acceleration estimator is 70 degrees per second squared. In the second experiment, we first simulated the result by our dynamic model with the known inputs, and then we compared it with the experimental result. The comparison is shown in figure below. The simulated result agrees with the experimental result, so the model is verified. At last, we tested our platform in the real water surface. The solar tracker is mounted on a buoy to float on the surface. We collected the motion of the buoy by IMU, and the date is shown in the right figure. The average of the absolute value in roll, pitch, and yaw are 6.23 degrees, 3.49 degrees, and 4.29 degrees, respectively, and the experimental result is shown in the figure below. We can see that the system is able to adjust to the desired altitude in 28 seconds. The bottom part takes 70.5 seconds, while the upper part leaves 10.5 seconds, and the whole system takes 0.35 seconds on average for the adjustment of 1 degree. Note that the result is not like the result from the in-room experiment, because the solar panel is affected by the disturbance from winds. This is a video demonstration of the proposed solar tracker. The first demonstration is an in-room experiment. We can see that the proposed solar tracker can be adjusted in 2 degrees of freedom, even when the input only have 1 degree of freedom. And this is the demonstration when the proposed solar tracker is working on the real water surface. That's all. Thanks for your attention.